if this looks a little bit weird today, but indeed the lighting is, let me check. All the lights are on. Okay. I have some lipstick on, so I'm calling this a Lipstick Physics Live. Hopefully I will see many of you here today. I have this necklace on, a red dress on, some other accessories on, and I'm ready to get this show started. So here we are. Welcome one, welcome all. Whoever is the first one to join. Hello, Pop Tarts. How are you? 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 Welcome one, welcome all. Welcome Europe, welcome Africa, welcome Asia, welcome South America, welcome North America, welcome Africa. I think I already said it. Welcome Antarctica, Australia, New Zealand. Hello, hello, hello. Hi, Pop Tarts. How are you? How's everybody doing? Again, did I not say the Africa continent already? So, hi, El Challen. I'm going to share the live now because I generally forget. Here I am, waiting for you. Today, I might even sing. I know it's been requested some lately. So Pop Tarts, El Challen says cha cha chow. Hello, 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 hello. Yes, I have some lipstick on. I even have it with me if anyone asks what kind. I'm ready. I'm ready. I'm here. I'm ready and I'm here. So let me share the live. Oh no, the little robot is getting, here, let me put the phone on do not disturb, if I can do that, because indeed, Baji is messing with the little robot as we speak, and I'm getting notifications about how he's interrupting its cycle as I speak here with you guys. Hello, Miriam. Hello, Pop Tarts. Hello, El Challen. Hello, Miriam. Sorry. I read that as Felipe with the L, so I said Miriam. Hello. Oh, hello, my name is Lara. Hello, Lara. Good evening. Good evening, good morning, good afternoon to everybody. We're just getting started. The live is about to get rolling here. I'm going to share it to my channel and say, we are live. Gunner Pack says hello, hello. Everybody do put something in the chat. Say hi, say hello, say anything you want, and I'll read it out loud and I will say your comment. Miriam says su brasileira, now entendo muito inglês. So I'm not sure exactly what what that means, but hopefully I kind of got it. DJ says, stop singing. Hi, DJ. How are you, my love? Your voice, Loki, sucks. That's, I think you forgot the Y there. But go ahead. El Challen says, anything you want. Anything you want. As in who? Who? Anything who wants. Anybody else, my darlings? Want to say hi, hello? Anything in the chat? Put it in there. Put it on the chat. I'll read it, give you a shout out, and then we will move on to our topic for today. Mr. Meme R says, what about me? You're ignoring me. Hi, Mr. Memer. Which one are you? I didn't see your message until now. I'm still sharing the live. Yay! We're live. We're live. You said say anything you want. The paragraph comments. So I don't see the paragraph comments. Maybe it's been held by YouTube. So I don't see anything from you, Mr. Memer, other than these comments. Okay, we're live. I'll tell the channel. Nathan, how are you? That smells like pee. I wonder if the kitty cats are getting into some kind of trouble in the bathroom with the litter robot. Huh. Interesting. We might have a pee situation. Miriam says bye-bye. Hi, Miriam. Bye, Miriam. Thank you for visiting. Really appreciate you. Mr. Memer, the paragraph comments. Nathan says hello, B. Hi, Nathan. What's up? Shall we do some more cosmology E type of reading? Is that what sounds good? Ooh, and I forgot to say, can we get 10 likes? Very pretty tonight. Thank you. Ooh, let me see if the green screen will work today or not. Does it work? I think it doesn't work, does it? Yeah, it's fine. Hi, Baji. Gunner Pack says, I'm Brazilian. I don't understand much English. Oh, that's okay. Welcome to Brazil. Welcome, welcome, welcome. It was green. Yeah, I know it turned green, but I was trying to see if I can show a picture in the background. I know you can see the comments, but you're ignoring it. Mr. Memer, I don't see your comments. So, it was green. Gunner Pack says no. I mean, the person that said those words said that. Okay. Ooh, can we get 10 likes and then can we get 20 likes? Oh, no, 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 no. No, 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 no. And then I'm going to pin this myself. Oh, thank you, Gunner Pack. Thank you for translating. Thank you. Okay, I'm going to get started. I think we'll continue with the Brian Greene book, The Elegant Universe, and I'll read from there. And we'll cover certain topics and I will explain them. So we'll get started with that. Thank you for the likes, guys. Let me share again. Hi, Stephen. Hi, Batshite. Hello, Stephen. Hello, everybody. You know what? I might even open a window because it's a little stuffy in here. And Baji, I can kind of smell something that I shouldn't be smelling. So I hope that you haven't made a mess. Okay. So remember how we were talking about string theory from Brian Greene's book, and we also talked about some of the major conflicts amongst physicists of different scales here in the book. So for example, physicists who work on very small stuff like atoms, subatomic particles, versus physicists who work on very big things such as stars, galaxies, and such. Thank you, Nathan. Hello, everybody. So that's sort of what we were talking about. And then the next part of this is called The Universe at its Smallest, What We Know About Matter. So I was gonna try to skip through some of the particle physics from this book because it's kind of like review. We have seen a pretty good review of particle physics recently from Stephen Hawking's book, A Brief History of Time. But I think oh my gosh, no, I didn't know about that. I did not know about that, Stephen. I'm so glad she came back. Oh, that's very scary. Mr. Memer, if you're gonna be a little weird, you may want to get it out of your system in the comments now, because when the mods are here, I don't think they will like you very much. Luna probably, oh gosh. So, as I was saying, basically some of the particle physics review that we got from Stephen Hawking's book is pretty good. But we will take a look at what Brian Greene is saying here, because some of it might actually be quite helpful and sort of complementary to what we already learned about from the Stephen Hawking book. So here we go. Universe at its smallest, what we know about matter. The ancient Greeks surmised that the stuff of the universe was made up of tiny, uncuttable ingredients that are called atoms. So it's sort of a Greek concept here, the atomic concept. Mr. Brother found her in our yard last night. I was so happy to see her today. She's been fixed. Okay, so there's no more children from Luna. I see. Well, I'm so glad you found her. Very nice. Thank you for sharing. Could we get 10 likes? Did everybody here like the live? Can we get 10 likes, and then can we get 20 likes, please? Thank you. Thank you so much. So this uncuttable word, Greek, it means atoms. Just as the enormous number of words in an alphabetic language is built up from the wealth of combinations of a small number of letters, they guessed that the vast range of material objects might also result from combinations of a small number of distinct elementary building blocks. It was a prescient guess. More than 2,000 years later, we still believe it to be true. Oh, thank you. Thank you. You got my likes, says Steven. Like times 10 from me. Thank you. Really appreciate you guys. So nearly 2,000, more than 2,000 years later, we still believe it to be true, although the identity of the most fundamental units has gone through numerous revisions. So we still sort of believe in uncuttable units of matter, as in very fundamental particles that don't further break down into even more basic particles or even more smaller particles. But as far as which is the most small particle, that has undergone some revisions. You know, we might have thought that it was an atom, but turns out there are subatomic particles. You know, there's the nucleus. The nucleus has protons and neutrons. Turns out those actually break down further into even smaller particles called quarks. So those types of revisions have kind of been doing the rounds in particle physics ever since the late 1900s. So we will kind of see how Brian Greene further summarizes everything for us here. But it should be interesting how he sort of opines about these things. In the 19th century, scientists showed that many familiar substances such as oxygen and carbon had a smallest recognizable constituent. Following in the tradition laid down by the Greeks, they called them atoms. The name stuck, but history has shown it to be a misnomer, since atoms surely are cuttable. By the early 1930s, the collective works of J.J. Thomson. So remember Thomson, the guy who gave us things about the electron and whatnot. So Thomson, Ernest Rutherford, Niels Bohr, and James Chadwick had established the solar system like atomic model, which most of us are familiar. So these people really gave us sort of the initial understanding of what goes on within an atom. There's sort of like this, they came up with a sort of a solar system model of the atom with the nucleus in the middle and then electrons kind of orbiting that nucleus. And then these are also the names of the guys who really gave us a lot in terms of the quantum world. So that's what we are reviewing here. Far from being the most elementary material constituent, atoms consist of a nucleus containing protons and neutrons that is surrounded by a swarm of orbiting electrons. For a while, many physicists thought that protons, neutrons, and electrons were the Greeks' atoms. But in 1968, experimenters at the Stanford Linear Accelerator Center, so this is sometimes called SLAC, SLAC, making use of the increased capacity of technology to probe the microscopic depths of matter, found that protons and neutrons are not fundamental either. Instead, they showed that each consists of three smaller particles called quarks, a whimsical name taken from a passage in James Joyce's Finnegan's Wake by the theoretical physicist Murray Gell-Mann, who previously had surmised their existence. The experimenters confirmed that quarks themselves come in two varieties, which were named, a bit less creatively, up and down. A proton consists of two up quarks and a down quark, and a neutron consists of two down quarks and an up quark. So this is very review-y for us because we read about this already, but bear with me. It's okay to hear it twice. So we'll keep going and sort of go through this small physics section of Brian Greene. Everything you see in the terrestrial world and the heavens above appears to be made from combinations of electrons, up quarks, and down quarks. So everything, all the matter that we see, everything that consists of ordinary matter is really these electrons, the up quarks, and the down quarks. So because up quarks and down quarks make up protons and neutrons, so that's why we're saying that everything that we really understand ordinarily, matter-wise, is up quarks, down quarks, and electrons. Harley says, do you remember me and my brother Lee? I think so, maybe. The Lee sounds familiar. Can you say a little bit more about you so that I can remember? Do you remember me and my brother Lee? Oh, yes! Are you guys from California? Did we do like noodle stuff together? I think I do remember. You guys are from the West, right? Didn't we make like shin noodles together? Was that the live where you came? I do remember. And didn't we make chai? Well, I might have made chai. Yeah, it was winter. Yeah, I was making tea a lot back then. Yeah. I think it was like the month of November or December, and I was making tea almost every night. Yeah. I was making tea almost every night. So yeah, indeed that may have been the case. Thank you for being here. I'll get back to my reading, but keep on sending your messages. Ooh, and can you please like the live? Thank you for revisiting us. Thank you for being here. Thank you. Welcome. And please do like the live. Okay, so everything is made of the up quarks, down quarks, and the electrons. No experimental evidence indicates that any of these three particles is built up from something smaller. So we don't really know about anything being anything smaller than the up quarks, down quarks, and the electrons. We think that ordinary matter breaks down into these, basically. Thank you, Harley. But a great deal of evidence indicates that the universe itself has additional particulate ingredients. So we've looked at cosmology explanations and cosmic ingredients of how really the cosmos or the universe has 5 different things. These are photons, baryons, neutrinos, dark matter, and dark energy. Baryons basically include protons and neutrons. So this is another way of saying that ordinary matter is made up of protons, neutrons, electrons, but there is more types of matter than that, and there's more types of ingredients in the universe than that. So that's what this sort of thing is saying. So the universe itself may have additional particulate ingredients, probably does have additional particulate ingredients. In the mid-1950s, Frederick Rines and Clyde Cohen found conclusive experimental evidence for a 4th kind of fundamental particle called a neutrino, So that's the other thing. Hello, Wolfie. That's the other thing that we understand is the neutrino, a particle whose existence was predicted in the early 1930s by Wolfgang Pauli. So gives us another type of particle, and this is a rather elusive kind of particle that I've talked about quite a bit on the channel. This is what I studied myself, actually, and it only interacts through the weak nuclear force. Remember, there were the four fundamental forces: gravitation, electromagnetism, weak nuclear force, and strong nuclear force, and neutrinos only interact through the weak nuclear force. So it's a very introverted particle. Neutrinos proved very difficult to find because they are ghostly particles that only rarely interact with other matter, and average energy neutrino can easily pass right through many trillion miles of lead without the slightest effect on its motion. Wolfie says hello. Steven says hi, Wolfie. Yay, here we are. Small family. This should give you significant relief because right now, as you read this, billions of neutrinos ejected into space by the sun are passing through your body and the Earth as well as part of their lonely journey through the cosmos. So they do pass through lots of things, but they don't interact much with anything. So they'll pass right through us, right through the Earth, right through anything. But we don't really feel anything because they are not interacting with us, with most of the things that are in the way, because those things are basically not really in the way for them. Neutrinos can just pass through, right through these things. This should, in the late 1930s, another particle called a muon, identical to an electron except that a muon is about 200 times heavier. So electrons are leptons, as we know that there's 3 different particle classes: leptons, quarks, and bosons. So electron is a type of lepton, neutrino is a type of lepton, and muon is a type of lepton. So in the lepton family, we actually have something called the muon, which is quite a bit heavier than the electron, but it belongs to that same family. So I don't want neutrinos in me. Well, they're not in you, they're just passing through you. You can't really avoid them too much because the sun makes a lot of neutrinos. So I sometimes give the analogy of chemical reactions. You know how all of chemistry will involve electrons in the processes of each chemical reaction. There is an electron that's being exchanged or something. Neutrinos are sort of like that in nuclear reactions. It's very difficult to have one without neutrinos coming out in some kind of way, or some neutrino being on either side of that reaction. So because the sun is a star, and by definition it has a nuclear reactor in its belly, that's how it's making light and energy and heat and all of that for us to live off of. The sun does a lot of nuclear reactions. It's burning hydrogen to make helium. That's a nuclear reaction. As in, it's a reaction or a process at the nuclear level. The nuclei of hydrogen are taken, which is just protons mostly. It could have neutrons if it's an isotope of hydrogen, but hydrogen nuclei are taken and then converted to helium nuclei. So it's a nuclear reaction, many nuclear reactions that the sun is constantly doing. And in all of these, it's very common to make neutrinos as a side product in these nuclear reactions. So it's very difficult to avoid neutrinos. But fear not, the neutrinos that are coming out of the sun are pretty low energy. So nothing to worry about. They're not going to hurt you or anything like that. Okay? More likely to be hurt by the photons probably that are coming from the sun, depending on which energy photon that you interact with, and whatnot. So yeah. So the neutrinos are fine. The ones from the sun are mostly all fine. They're not very high energy. So in order to make the types of neutrinos, for example, that I was interested in for my thesis are the types of neutrinos that are very high energy. We call them ultra high energy neutrinos. So you need a very, I mean, depending on, the type of neutrino. Basically, if it's an astrophysical neutrino versus a cosmogenic neutrino, and there's a couple different processes. But basically, you need a way to accelerate the neutrino to a very, very high energy, and for it to be made in a very exotic or high energy type of explosion or cataclysmic event in the sky, and then to be accelerated, and then to be sort of spewed out, and then to travel all the way across the skies to us. That could be a way to get ultra high energy neutrinos. It's not entirely confirmed, although we have found high energy neutrinos, like quite a bit high energy neutrinos, but not maybe the ultra high energy ones yet. But those types of neutrinos, even those ones, they would just make little particle showers in whatever medium. We were looking for those neutrinos in the ice, actually, in the Antarctic ice. They were hypothesized to maybe interact with the material in the ice, with the ice basically, with the dielectric medium of the ice. And they would make some particle showers. We would get maybe Cherenkov radiation, blah, blah, blah. Those were, that was going to be the detection method. So to get neutrinos, even those very extreme energy neutrinos, to get them to interact enough to then get a detection out of that is very difficult. So nothing to fear. When I said the neutrinos are passing through us, it means that we are transparent to most low energy neutrinos. There is sort of a cross section of interaction of these neutrinos, and in certain energy regimes, it's been shown, well, it was theorized and then probably shown that depending on the energy of the neutrino, you would get higher and higher cross section. So with the energy, your cross section would go up. And so then if you're below that sort of energy, for example, for these sun neutrinos, there is the cross section of interaction is extremely low, meaning that they don't really interact with anything along the way. It's kind of like if we could just pass through something as if it didn't exist, So that's what the neutrinos are doing. It's a very, it's difficult to intuitively understand because they're very tiny particles. They were thought to be almost massless, but they're not entirely massless. And depending on their energy, because they don't interact, it's almost like they're not there. You know what I mean? And that's why it's difficult to detect them, find them, etc. So anyway, okay. So this should give you significant relief because right now, as you read this, billions of neutrinos ejected into space by the sun are passing through your body and the earth as well as part of their lonely journey across the cosmos, through the cosmos. So lonely journey as in they don't interact with anybody. In the late 1930s, another particle called a muon, identical to an electron except that a muon is about 200 times heavier. So a muon is very much like the electron, but it's 200 times heavier. And as we shall see, they also have sort of a decay time that's much faster. And so you might not really meet too many muons in nature, in the wild either. But that too is a natural particle that can be made in certain processes and interactions. I've learned something new tonight. Thank you. Of course. Thank you for being here. So this muon, which is 200 times heavier than the electron, was discovered by physicists studying cosmic rays, which are showers of particles that bombard Earth from outer space. Because there was nothing in the cosmic order, no unsolved puzzle, no tailor-made niche that necessitated the muon's existence, The Nobel Prize winning particle physicist Isidore Isaac Rabi greeted the discovery of the muon with a less than enthusiastic, "Who ordered that?" Nevertheless, there it was, and more was to follow. So basically, they discovered a new type of particle, and some people were like, okay, so like, who ordered that? What does it give us? What does it mean? Is this anything special? Because it turns out that muons are just sort of a heavier version of an electron, as we shall see. I mean, I don't know if they will, I don't know if he tells us, let's see. Does he give us, I thought he might give us the decay time of a muon. I think it's, I mean, it's only, if I remember correctly, it's around 2.2 microseconds or something, but please do verify that. I'm kind of searching my memory for the decay time of a muon. But basically, even if you make a muon, it's not like it will be stable forever. It decays. And so, you know, in certain extreme situations, in these cosmic ray interactions, again, you might make a muon, but it is to be seen exactly how long it will remain stable as a stable particle, enough for us to recognize it as a particle. That's the question. So using ever more powerful technology, physicists have continued to slam bits of matter together with ever increasing energy. So that's the other thing, is that if you smash things together, if you create sort of these human-made accelerator type of environments, which we obviously do, such as at the Large Hadron Collider, nature has certain accelerating environments as well. And those also create particles, and those also accelerate particles that we wish to detect. But we probably haven't, you know, exhausted all the types of particles that we could get from such accelerators. But here on Earth too, we made a number of these colliders where we smash together particles, we accelerate them, and those types of extreme environments can also create certain particles, even if they're going to decay, but say for a few nanoseconds, microseconds, whatever, you might just create a new type of particle that then you could be like, oh, well, what's this? What does this do? And does this account for some other mystery? So I believe the muon is, I believe it's in the microseconds. So Stephen, can you look up the lifetime of a muon, please? That would be most excellent. Is it 2.2 microseconds or something like that? Because I wanted to just kind of say how, once you make a muon, for how long can you see it? As in how long before it decays? Because it does decay to muon, M-U-O-N. He gives a table for the electron, muon, and tau particles, and he gives the mass, but he does not say readily what the decay time is, and I just want him to say it so that I don't have to look it up. But I think it's in the order of a couple microseconds for the muon. Okay, so using ever more powerful technology, physicists have continued to slam bits of matter together with ever increasing energy, momentarily recreating conditions unseen since the Big Bang. In the debris, they have searched for new fundamental ingredients to add to the growing list of particles. Here is what they've found: 4 more quarks. So we have more quarks, as we know: charm, strange, bottom, and top. Those are the names of the other quarks that we found. Ooh, yes, 2.197. Is it seconds? Oh, that's quite long. Sorry, now I have to look it up. Is it seconds? I thought it'd be like, why did I think that it is microseconds? It is so I think you mean microseconds, right? Muons have a mean lifetime of about 2.197, like you said. it's actually microseconds, so 10 to the minus 6 seconds, okay, before decaying into an electron and 2 neutrinos. So even muons, by the way, once they decay, they will make neutrinos. So pretty much anything, any nuclear reaction, any decay type of thing, some lepton decaying to a lighter lepton, everything and anything makes a couple of neutrinos along the way. So neutrinos are very abundant. They're made a lot in a lot of different processes, but they don't do much. They don't interact much with anything. So they're safe for the most part, you know, depending on the energy of them, which is, it's difficult to find ones that are very high energy. So we're okay. So here we go. Here's Google. Muons have a mean lifetime of about 2.197 microseconds. So like I was saying, 2.2. So I rounded up a little bit, but I said 2.2 microseconds. And I was right. Oh, thank gosh. Oh, thank gosh. But I wanted to check. So thank you, Stephen, for checking. Are you going on a date? I am not. This is it. I'm coming to the live, and here we are. Thank you for being here, John Foster, Stephen, everybody. Thank you so much. Can you please like the live? Can we get 10 likes, and then can we get 20 likes? I'm a little sad about how few people are here on my lipstick live, but you know, that's okay, I suppose. I got it wrong. It was microseconds. I looked again. Of course, that's fine. Yeah, I figured that it's 2.2 microseconds for the decay time of a muon. So here we go. Unstable particle. Muons are unstable subatomic particles, meaning they don't exist indefinitely and eventually decay into other particles. So there are certain particles that are in these particle families like leptons, quarks, and bosons. So this muon example is a lepton example. They belong to the same family of particles as electrons. So muons, electrons, taus, and then the neutrino flavors. There are 3 neutrino flavors. They all belong to the same particle family called the lepton family. And then there's the particle family called quarks, and then there's the particle family called bosons that we've talked about. So these 3 families, right? But some of the particles within these families, such as muons in the case of the leptons family, is sort of an unstable particle. So because its decay time, like Stephen has pointed out, has Googled here, is 2.2 microseconds. So pretty much it's unstable. You're not going to indefinitely see it be stable and chilling in nature forever, just like electrons do, you know, protons do, neutrons do. So like those quarks that make up the protons and neutrons basically are in a way, you know, stable. They're interacting with each other in those sort of bound states of forming the proton and the neutron, and we see them to kind of just like be and exist in nature normally, naturally. But a muon, if you made one, even if it was naturally made or artificially made, it's gonna decay after on average time of 2.2 microseconds. So it's not quite really considered, it's not really a very stable particle. So when a muon decays, it transforms into an electron or a positron, a muon neutrino, and an electron antineutrino. So it's going to make, you know, some kind of electron or positron thingy thing and a couple of neutrinos, electron or positron, depending on whichever way. The mean lifetime of a muon is the average time it takes for a muon to decay, which is about 2.197 microseconds, so around 2.2 microseconds. Due to the effects of special relativity, the decay time of muons can appear longer when measured by an observer in a different frame of reference, particularly when the muon is moving at speeds close to the speed of light. So very interesting fact, because time is relative. So depending on your frame of reference, if the muon is moving very fast, then its decay time could appear to be longer. The decay of muons provides evidence for the principles of special relativity, specifically time dilation. So super interesting. Muons are produced in the upper atmosphere when cosmic rays collide with atmospheric molecules. So by the way, we've actually covered an example, a very famous example of a cosmogenic interaction which makes muons. Now, of course, muons will decay further into electron or positron and neutrinos, but we do make them naturally. It's just they're not a very stable particle. The decay of muons follows an exponential distribution, meaning that the probability of a muon decaying at any given time is proportional to the number of muons that have not yet decayed. And there you go. That's a little bit of a quantum probability E type of thing for you, because muons are tiny, and so they follow tiny physics laws, which is probabilistic in nature. Okay, using all right, so here's what they found as far as the quarks. We've got charm, strange, bottom, and top. Some weird names, but there you go. And another even heavier cousin of the electron called a tau, as well as two other particles with properties similar to the neutrino called muon neutrino and tau neutrino. So we've got, among the leptons, we've got electron, muon, tau. Then we've got electron neutrino, muon neutrino, and tau neutrino. So three flavors of neutrinos, which we named electron, muon, and tau neutrinos. The quarks, I named them up, down, charm, strange, bottom, and top. And then we also have bosons. We'll see what he talks when he mentions those, but those are the other type of family of particles. These particles are produced through high energy collisions. So what he means is these extra particles that we just mentioned. These particles are produced through high energy collisions and exist only ephemerally. They're not constituents of anything we typically encounter, but even this is not quite the end of the story. There's even more. So if you thought that we're discovering quite a few particles and, is this the end of the story? Then not really. Each of these particles has an antiparticle partner, a particle of identical mass but opposite in certain other respects, such as its electric charge, as well as its charges with respect to other forces discussed below. For instance, the antiparticle particle of an electron is called a positron. It has exactly the same mass as an electron, but its electric charge is +1, whereas the electric charge of the electron is -1. So it has the opposite charge as the electron, the positron. And we talked about how in nature we have, in a different life, we talked about how in nature we have more electrons than positrons because there's more natural processes making electrons than there are making positrons. And poor positrons have been annihilated at various stages of this universe, so that we have very few of them, and we have very many more of the electrons. Okay, when in contact, matter and antimatter can annihilate. 1 second, let me shift the bar stool a little bit. Okay, here. So matter and antimatter can annihilate one another to produce pure energy. That's why there is extremely little naturally occurring antimatter in the world around us. So basically, sometimes particle and antiparticle pairs will annihilate and just make some photons. And so because this particular process of a particle antiparticle annihilating each other and just making photons is quite common, this is one way in which positrons actually have been taken out of the mix of things. They've been kind of annihilated and gotten rid of, whereas there were other methods of producing electrons. So electrons were able to stick around, be produced, be a thing that we know and love, whereas positrons we're less familiar with, right? Because they're not as abundantly found in nature. They're not as common. We know that it's the weird antiparticle partner of the electron, but how often do you really meet a positron, right? So that's sort of the thing with the antiparticles. Physicists have recognized a pattern among these particles displayed in table 1.1. Okay, we will take a look. All I see is the names of the particles, their masses, and whatnot. Okay, each family, the particle or the matter particles neatly fall into 3 groups, which are often called families. I think I just mentioned the families, and hopefully that's what he's doing too. Each family contains 2 of the quarks. Oh. Oh, I see. The three families of fundamental particles and their masses in multiples of the proton mass. I'm going to show you the table, so don't worry, but the values of the neutrino masses have so far eluded. When he wrote the book, I think they did not have neutrino masses yet. Or they maybe just had error bars or something. Oh dear. I see. Okay, let's see what he's saying. I see. I don't know if I would, organize the particles quite like that. But okay, let's just see what he's saying. Let's see what the string theorist has to say about particles. Each family contains two of the quarks, an electron or one of its cousins, and one of the neutrino species. The corresponding particle types across the three families have identical properties except for their mass, which grows larger in each. I see. Okay. That all of this is to say there's electron, neutrino, up quark, down quark, right? So electron, we know what that is. Electron, neutrino, it's a type of neutrino. Up quark, down quark, those make up protons and neutrons. Then we come over, we've got muon, neutrino, charm quark, strange quark. So it's kind of like just saying that, okay, leptons, in the leptons we have muon and muon neutrino. We have charm quark and a strange quark, which are heavier than the up quark and down quark. Then we come over to the third column, we have tau neutrino, top quark, and bottom quark. And these are, again, all heavier than the middle column. So the columns basically just get kind of heavier in the masses of these particles. But tau neutrino, those are leptons. So this is not really how I organize things, or I would organize things. I would just say that leptons are the electron, muon, tau, and the electron, muon, and tau neutrinos. Those three flavors of neutrinos, those are the leptons. Quarks are up, down, charm, strange, top, bottom. And then I would mention the bosons, which are the third family of particles. I wouldn't really do this table, but this table does give you the masses of the particles. And yes, like he said, those masses are increasing when you go from electron to muon to tau. And I think from electron neutrino to muon neutrino to tau neutrino, and then up quark to charm quark to top quark, and then down quark to strange quark to bottom quark. So these things are heavier. Top is heavier than charm, is heavier than up. Bottom is heavier than strange, is heavier than down. Okay, or you could just have a different way of organizing the particles and kind of just look up their mass, because not everybody's going to remember every particle's mass, because there's so many particles. So it's all good, however it works. The upshot is that physicists have now probed the structure of matter to scales of about a billionth of a meter, and shown that everything encountered to date, whether it occurs naturally or is produced artificially with giant atom smashers, consists of some combination of particles from these three families and their antimatter partners. Okay, so the arrangement into families at least gives some semblance of order, but innumerable whys leap to the fore. So this type of sort of the particle jungle that I presented you with, if you're thinking that, oh my gosh, you just mentioned a lot of particles, electrons, muons, taus, electron neutrino, muon neutrino, tau neutrino, up quark, down quark, strange quark, charm quark, top quark, bottom quark. This is just a ton of particles and a ton of particle names, and they all have different masses. Like, what's really going on? What's the more fundamental, more broader theory of these things that can kind of subsume these particles and their theories? And can we just get to that part, because this is way too many parts. See, some people don't mind that the particles, there's this particle soup of particles, there's this particle jungle of very many particles, but some people do mind because they think that, well, learning about these particles and how very many of them there are, is it really helpful if I don't understand why these particles are a thing, and what's the sort of more broad theory that might explain all of this. So that's sort of, I think, what he's getting to here. Why are there so many fundamental particles, especially when it seems that the great majority of things in the world around us need only electrons, up quarks and down quarks? So that's the other thing too, is that ordinary matter, most of the things that we encounter, is just really electrons, up quarks and down quarks, in the sense of that protons and neutrons are up quarks and down quarks combined, and electrons are electrons. That's a fundamental particle, thank goodness. You know, most things, most ordinary matter is just electrons, protons, neutrons. So electrons, up quarks and down quarks. So how come we're finding these other types of particles, and how come that they're not really, they don't seem to be as, common in nature? So why are there 3 families? Why not 1 family or 4 families or any other number? Why do the particles have a seemingly random spread of masses? Why, for instance, does a tau weigh about 20 times as much as the electron? So that is almost over 3,000 times the mass of the electron. Why does the top quark weigh about 40,200 times as much as the up quark? So again, top quark is very much more massive than the up quark. So, electron we see in nature, but this other thing, the tau, is a type of particle also in the same family of leptons as the electron, which seems to be much, much heavier than the electron. Of course, it decays, it's not a very stable particle, etc. But, it's much heavier. Why is that? What is the top quark, which is another type of quark? Why is that so much heavier than the up quark? Did they occur by, these are strange, seemingly random numbers. So these masses, these things that we have found, did they occur by chance, by some divine choice, or is there a comprehensible scientific explanation for these fundamental features of our universe? So it's almost like we're taking, when you consider these different types of particles in the particle jungle that we know of, the electron, muon, tau, the electron, neutrino, muon, neutrino, tau, neutrino, the quarks, all that, it does seem a little bit like we're finding sort of snapshots of nature a little bit randomly. We're making measurements of maybe some things that are sort of in that state. And as we mentioned, some of these particles are not even really stable for that long, etc. So is it that we're kind of like chancing upon them? They're just kind of there and we see them in that state for a bit. And is this sort of some random chance thing, and maybe there's even more particle possibilities that we just haven't found because we haven't chanced upon those or something? Once you start to find so many, it begs the question, well, could there be another experiment then that finds another particle or something? And is finding the particles as important as it is to understand, well, what's really going on? What's the underlying insight into all of this, which would explain all of the things, all of the particles, all of the everything, without having to go into each one specifically? Am I the only person in here? I don't know. I think there's a few more. But thank you for being here. Have a good evening. Hopefully this is helpful. So, we talked about the leptons and the quarks so far. In the next section, we'll talk about the bosons. But I'll just say that the bosons, we've already mentioned, those are the photons and other bosons that are basically the force carriers for all these particles that we mentioned so far. So we've got the strong force. The force particle for that is gluon. We've got the electromagnetic force. The force particle for that is, of course, our well-loved photon. We've got the weak force. The force particle for that is weak gauge bosons. These are the W and Z bosons. And then we have got the gravitation force that we also know and understand, at least to some extent. And the force particle for that, we call that the graviton. But its existence has yet to be confirmed experimentally. So we don't really have a graviton. We just think that there should be one because it's a force, it's a fundamental force of nature. So where is it? That type of thing. But you know, not sure. Not sure where it is. It's not been really found. Whereas the other ones have been found. Okay. So let's see what he says here. Gravity is the most familiar of the forces, being responsible for keeping us in orbit around the sun, as well as for keeping our feet firmly planted on Earth. The mass of an object measures how much gravitational force it can exert, as well as feel. The electromagnetic force is the next most familiar of the four forces. It is the force driving all of the conveniences of modern life, lights, computers, TVs, telephones, and underlies the awesome might of lightning storms and the gentle touch of a human hand. Microscopically, the electric charge of a particle plays the same role for the electromagnetic force as mass does for gravity. It determines how strongly the particle can exert as well as respond electromagnetically. And then he talks about the strong and weak forces. These are less familiar because their strength rapidly diminishes over all but subatomic distance scales. So the strong and weak forces are sort of, they're at play at a different sort of length scale than what we would interact with. So we don't really see them much. In our scales, we more interact with gravitation and with the electromagnetic force. So they're the nuclear forces. This is why these two forces were discovered only much more recently. The strong force is responsible for keeping quarks glued together inside of protons and neutrons. So, you know, the force that's sort of gluing together protons and neutrons, or the quarks really within protons and neutrons, is the strong force. And keeping protons and neutrons tightly crammed together inside atomic nuclei. So that's why sometimes, the force is called gluon, the force particle is called gluon. So it's a strong force, or the strong nuclear force is the name of the force. But the force particle boson that's carrying that force is called a gluon, because they're gluing together the quarks and keeping the nucleus together. So the weak force is best known as the force responsible for the radioactive decay of substances such as uranium and cobalt. During the past century, physicists have found two features common to all these forces. At a microscopic level, all the forces have an associated particle that you can think of as being the smallest packet or bundle of the force. If you fire a laser beam, an electromagnetic ray gun, you're firing a stream of photons, the smallest bundles of the electromagnetic force. So that's how we can think of it. Similarly, the smallest constituents of weak and strong force fields are particles called weak gauge bosons and gluons. The name gluon is particularly descriptive. You can think of gluons as the microscopic ingredient in the strong glue holding the atomic nuclei together. And by 1984, experimenters had definitively established the existence and the detailed properties of these three kinds of force particles recorded in table 1.2. So that's where this table is. I can show you that in just a sec. Physicists believe that the gravitational force also has an associated particle, the graviton, but its existence has yet to be confirmed experimentally. So that's sort of where we understand the electromagnetic force, the strong nuclear force, and the weak nuclear force to some extent, and we even found a sort of theme that unifies them, and we talked about that in the other book as well, in Stephen Hawking's book. But when it comes to unifying these three forces with the gravitation force, gravitation being an extremely commonly encountered and commonly understood type of force, there isn't much luck there. So that's a big gap as well, is that these three types of forces, electromagnetic force, strong and weak nuclear forces, those three and gravitation are sort of not really unified at all by anything. And that's a problem. Basically, we want more unification. We want more understanding of something broadly and something that explains all of this, sort of the theory of everything. These are the four fundamental forces. What's the theory of everything that can bring this all together? Explain to me what is going on What in the heck is going on with these four forces? And that's the issue that we are not able to address so far without a grand unified theory. But string theory is a candidate that tries to do that, I believe. We'll see. We'll see what Brian Greene says about that. So the second common feature of the forces is that just as mass determines how gravity affects a particle and electric charge determines how the electromagnetic force affects it, particles are endowed with certain amounts of strong charge and weak charge that determine how they're affected by the strong and weak forces. These properties are detailed in the table in the endnotes to this chapter. Okay, let's see, where are the endnotes? Okay, we'll see later. But as with particle masses, beyond the fact that experimental physicists have carefully measured these properties, no one has any explanation of why our universe is composed of these particular particles with these particular masses and force charges. So that's the thing. We don't really understand the why of these particles. We sort of know them, we've seen them, we've observed them. We did experiments that created them, or experiments where we observed them for the first time and we discovered them, and Nobel Prizes were given for these discoveries. Good, all good. But we don't have an overarching theory that explains why these particles are even a thing. The deeper insight about them is still sort of missing, is the point of this author. Hi, Peter. Peter says, I've been here for a bit listening. Oh, good. Hello, Peter. Notwithstanding their common features, an examination of the fundamental forces themselves serves only to compound the questions. Why, for instance, are there 4 fundamental forces? Why 4? Why not more? Why not 5 or 3 or perhaps only 1? Why do the forces have such different properties? Why are the strong and weak forces confined to operate on microscopic scales while gravity and the electromagnetic force have an unlimited range of influence? So that is something common between electromagnetism and gravitation, is that they're very long range. Now, of course, gravitation is weaker than the electromagnetic force, but still very long range. Another thing about gravitation is that it's always only attractive, whereas electromagnetic force has both attractive and repulsive nature, depending on opposite charges or like charges. So, some similarities and some differences even between those two forces that are usually well understood, but still, it's still a bit of a mystery why there are these forces, to appreciate, and why do the forces have such different properties? Why are the strong and weak forces confined to operate on microscopic scales while gravity and the electromagnetic force have an unlimited range of influence? And why is there such an enormous spread in the intrinsic strength of these forces? To appreciate this last question, imagine holding an electron in your left hand and another electron in your right hand, and bringing these two identical electrically charged particles close together. Their mutual gravitational attraction will favor their getting closer, while their electromagnetic repulsion will try to drive them apart. Which is stronger? There is no contest. We already know. By the way, do you know which is stronger? Have you been paying attention? We already know who's going to win. The electromagnetic repulsion is about a billion. So 10 to the 42 times stronger. If your right bicep represents the strength of the gravitational force, then your left bicep would have to extend beyond the edge of the known universe to represent the strength of the electromagnetic force. Wow. Quite a workout there. The only reason the electromagnetic force does not completely overwhelm gravity in the world around us is that most things are composed of an equal amount of positive and negative electric charges whose forces cancel each other out. On the other hand, Since gravity is always attractive, there are no analogous cancellations. More stuff means greater gravitational force. But fundamentally speaking, gravity is an extremely feeble force. This fact accounts for the difficulty in experimentally confirming the existence of the graviton. Searching for the smallest bundle of the feeblest force is quite a challenge. Searching for the smallest bundle of the feeblest force is quite a challenge. So we still don't have a graviton discovered yet. Isn't that crazy though, the 10 to the 42 times stronger thing? Experiments also have shown that the strong force is about 100 times as strong, 100 times as strong as the electromagnetic force, and about 100,000 times as strong as the weak force. But where is the rationale for our universe having these features? That is wild. Yeah, very wild indeed. This is not a question born of idle philosophizing about why certain details happen to be one way instead of another. The universe would be a vastly different place if the properties of the matter and force particles were even moderately changed. For example, the existence of the stable nuclei forming the 100 or so elements of the periodic table hinges delicately on the ratio between the strengths of the strong and electromagnetic forces. So, you know, if the electromagnetic force was more and there was more repulsion, that could have been an issue. If the strong force was more or less, that could have been an issue forming the nuclei of all these elements that we have in the ordinary matter, right? So all of this stuff actually affects our everyday life very, very much. So we'll see. We'll see what this section holds here. So, for example, the existence of the stable nuclei forming the 100 or so elements of the periodic table hinges delicately on the ratio between the strengths of the strong and electromagnetic forces. The protons crammed together in atomic nuclei all repel one another electromagnetically. So guess what? The protons in all these nuclei, and of course, the heavier the electron, or sorry, the heavier the element, the more protons you're going to have in that nucleus, right? Of course, the heavier elements also have neutrons, but basically protons have a charge. It is they're all positively charged, so this positive charge will repel each other electromagnetically. But thank goodness for the strong force, otherwise that would have been an issue. So how come we have the very strong repulsion between protons in a nucleus, but somehow they still are in the nucleus together forever happily, right? In stable nuclei of stable elements in the periodic table. Entire chemistry, is hinging on that. So the protons crammed together in atomic nuclei all repel one another electromagnetically. The strong force acting among their constituent quarks, thankfully, overcomes this repulsion and tethers the protons tightly together. But a rather small change in the relative strengths of these two forces would easily disrupt the balance between them and would cause most atomic nuclei to disintegrate. So if you have too much repulsion between the protons, which is not countered by the attraction between quarks that make up those protons and neutrons. And actually, guess what? The neutrons are also part of that picture. The neutrons also are made up of quarks, and those quarks also provide strong force interaction, right? Strong nuclear force interaction. So, left to themselves, the protons would probably not want to be very close together because they're all like charges, they repel each other. But there's also neutrons in the mix of things, and protons and neutrons are both made up of quarks, which interact with each other through the strong nuclear force, and the gluon force carrier particle is literally gluing together protons and neutrons. And this is very important in the heavier elements especially as well, because remember, this is actually important for stars and how stars die, because if it becomes too difficult to keep making more and more stable nuclei, then you're actually going to stop doing nuclear reactions within stars. And that's actually how a star can run out of its nuclear power. Okay. So things like nuclear binding energy and things like that that we have talked about in the past are sort of at play with all this. Okay. So the protons crammed together in atomic nuclei all repel one another electromagnetically. The strong force acting among their constituent quarks thankfully overcomes this repulsion and tethers the protons tightly together. But a rather small change in the relative strengths of these two forces would easily disrupt the balance between them and would cause most atomic nuclei to disintegrate. Furthermore, were the mass of the electron a few times greater than it is, electrons and protons would tend to combine to form neutrons. So neutrons can actually also disintegrate. Depending on its energy, a neutron can actually disintegrate to make a proton and an electron and some, guess what, neutrinos. So, if the electron was a little bit bigger in mass, then electrons and protons would tend to combine to form neutrons, gobbling up the nuclei of hydrogen, the simplest element in the cosmos, with a nucleus containing a single proton, and again disrupting the production of more complex elements. So if electrons were a little bit heavier and made neutrons a lot with protons, then that could have really disrupted the formation of heavier elements. And guess what? We are made of heavier elements. We're made of things like carbon, oxygen, all that, which are the heavier elements. The Big Bang just gave us hydrogen and a little bit of helium and trace amounts of lithium. So if we don't make heavier elements in environments like stars and in the first stars and galaxies, we would not be here. So this is a very, very important thing to appreciate, which is that it's a good thing that electrons and protons didn't get together too much to make neutrons, which could have disrupted and not made the heavier elements. So once again, were the mass of the electron a few times, I guess it would have to be a few times greater than it is, electrons and protons would tend to combine to form neutrons, gobbling up the nuclei of hydrogen, the simplest element in the cosmos, with a nucleus containing a single proton, and again disrupting the production of more complex elements. Stars rely upon fusion between stable nuclei and would not form with such alterations to fundamental physics. The strength of the gravitational force also plays a formative role. The crushing density of matter in a star's central core powers its nuclear furnace and underlies the resulting blaze of starlight. If the strength of the gravitational force were increased, the stellar clump would bind more strongly, causing a significant increase in the rate of nuclear reactions. But just as a brilliant flare exhausts its fuel much faster than a slow-burning candle, an increase in the nuclear reaction rate would cause stars like the sun to burn out far more quickly. So we actually know that massive stars require more fuel, obviously, to stay burning, but that also means that they burn out more quickly. This is sort of similar to that. So the more massive stars die younger, die more quickly, and then same thing here. So an increase in the nuclear reaction rate, if the nuclear reaction rate was a lot more, then things like our sun would burn out faster. Okay, so that's not good either. This is all very finely balanced in nature. I hope you're appreciating is that everything is kind of super duper finely balanced, and these nuclear rates and stuff should not be taken for granted in the sun, for example. So we can thank the universe for all this. And another thing is, on the other hand, were the strength of the gravitational force significantly decreased, matter would not clump together at all, thereby preventing the formation of stars and galaxies. So even though the gravitation force is quite weak compared to something like the electromagnetic force, obviously, it's still strong enough where some matter actually clump together to form the first stars and galaxies, because if that didn't happen, stars are where the heavier elements are made. So certainly we would not get the heavier elements and we would not be here, you know. So we could go on, but the idea is clear. The universe is the way it is because the matter and the force particles have the properties they do. But is there a scientific explanation for why they have these properties? These properties are very unique, very specific, very much finely balanced, which gives us the universe that we have, which gives us the world that we have, which gives us the heavier elements and everything else. But why is that? Is there a, again, bigger, broader theory that can explain all of this? And that's really the motivation for something like a grand unification theory, of which I believe string theory is a candidate. So we will see in the next part what he says about that. String theory offers a powerful conceptual paradigm in which, for the first time, a framework for answering these questions has emerged. According to string theory, if we could examine these particles with even greater precision, a precision many orders of magnitude beyond our present technological capacity, we would find that each is not point-like, but instead consists of a tiny, one-dimensional loop. Yes, we're talking about the motivation for string theory. Hi, Combat Sports. Gluons. We just talked about gluons, yeah. So you can rewind. Go back into so whatever you missed, you can rewind. Combat Sports. Go to the left. Rewind. We just talked about all the particles from the perspective of Brian Greene from his book called The Elegant Universe, which is mostly a review of what we already covered before, especially from Brief History of Time by Stephen Hawking. But we're just getting into sort of the motivation for string theory in understanding why all these particles are the way, why all these properties are the way they are, why the universe is so finely balanced, and everything like that. So we would find that each particle is not point-like, but instead consists of a tiny one-dimensional loop. A loop. L-O-O-P, loop. I see. Okay. Ooh, I think you would like string theory, right, Combat Sports? So I'm glad you're joining. We will continue this tomorrow, actually. We will wrap it up in a few minutes here. Like an infinitely thin rubber band, each particle contains a vibrating, oscillating, dancing filament that physicists lacking Gelman's literary flair have named a string. Oh, there's a picture here. We can look at this later. Ah, a string. String theory adds the new microscopic layer of a vibrating loop to the previously known progression from atoms through protons, neutrons, electrons, and quarks. The best part of quantum mechanics. Yeah. Although it is by no means obvious, we will see in chapter 6 that this simple replacement of point particle material constituents with strings resolves the incompatibility between quantum mechanics and general relativity. String theory thereby unravels the central Gordian knot of contemporary theoretical physics. This is a tremendous achievement, but it is only part of the reason string theory has generated such excitement. So let me show you the picture. I'm going to rotate the camera and let you look at this. Oh, actually, let me show you these glasses I got. I got these computer glasses that I'm supposed to show on a video. Blue light blocking by Cyxus. Cyxus. Okay, let's see what this looks like. I got the package and I haven't even opened it yet. Strong and weak interaction, my best part of quantum mechanics. I'm recording so I can listen to you again. I did get most of that. Oh, thank you. Testing kits. Okay. You're recording? Oh, how nice. Oh, by the way, you don't really have to record because all the live episodes are uploaded automatically to my channel. If you go to the live tab, so on my channel, if you go to a tab called live, every episode is available there, I believe, as a recording. So yeah, I'm recording so I can listen to you again. So if you would, you could go to my channel under the live tab and re-listen to all of the episodes, and that would actually help to support me a lot. So if you could do that, Peter, that would be amazing. And then leave your comments on these things, on these episodes, under the videos, under the live videos, / under the live upload videos. So this is America's leading computer glasses brand, Cyxus Technology Group Limited, unboxing video. Peter says, okay, look at this. Very nice glasses here, or very nice little box for the glasses. And now I'm opening it. This is my unboxing video right here for you guys for this thing they sent me. So thank you for your patience. What is this? Get the blue light torch from the package. Put the lens of Cyxus glasses above the testing area. Turn on the torch. Wow. Okay, I'm gonna do that later. Just wanna see what these glasses, oh my gosh! Wow. These are quite nice. Cyxus.com. These are quite nice, I must say. Very nice box and very nice glasses. Thank you, Cyxus. Okay. Oh, wow. Wow, look at that. Goodness. Oh my god. Oh my god. Okay, I'm gonna take my hairband off because I don't want too many interfering things here. So there we are, guys. This is my blue light glass. Oh my god. Oh my god. Do I look weird? Is this helping? I think so. Oh, hi. Hello, guys. Here's my blue light glasses, guys. You look nice, intelligent. Thank you. Thank you. Wouldn't want to look dumb. Thank you. Oh my god. Okay, I'm still getting used to this look. Maybe I can rock it. Everybody, class is in session. I have my blue light glasses on. They are the sponsor of this live. But it is a little different, actually. I can read your comments. You look nice, intelligent. Leave them on. Thank you. Thank you, thank you. Thank you. Thank you, thank you. I think I can definitely wear them sometimes. I got 3 pairs of glasses from America's Best. So, I think I like this what is it, tortoise shell design on the glasses. I really like that. It's pretty snug on my face. It's pretty good. Now I'm ready for all of the blue lights. And I think this is the testing kit that they sent to test that indeed the blue light is, oh gosh, what do I do here? Oh. Here, look at this. There's a blue light tester thing. They said, turn on the torch, beam the testing area through the lens about 2 seconds. The area hardly turns blue. Beam the area without Sykes' glasses. Okay. I'll do the thing with the thing. I don't know. Beam the testing area through the lens. What testing area? Oh. You know what? I don't know if I understand this test very well. But the glasses look pretty cute, I think. So there we go. But it's cool to have this blue light torch, I guess. I'll have to figure out what I was supposed to do with this. But thank you so much, Sykes. Keep on sending your stuff. Looks pretty good. Where are the cops when you don't need them? Okay, I'm gonna show you guys the picture that I promised. Okay, enough of this. I really like the cover. Thank you so much. Love the cover, love the glasses. Thank you so much. I'll make this into a short. Thank you. And a video probably. Yeah. Blue lights and cops. Yeah. I get it. Okay. All right. Ooh. Oh, look at this. There is like a nice little thing right there to put the glasses in, and they even gave me a nice oh, this is so nice, guys. Thank you. They gave me a little cloth thing. Aw. Oh my gosh. Oh, such a nice cloth for the glasses. Thank you so much for the gift. Okay. Alright, actually, I'm gonna leave them on for now. And then I'll show you the picture that I was talking about. I'll have to see how to do that. Thank you for liking the live. Can we get 20 likes? Thank you so much. Can we get 20 likes? I'm gonna put this and this over here. I didn't know if I was gonna do this today or not, but I ended up going with it. Where are your kitties? Oh, let me show you. Oh, Baji is looking so cute right now. Let me show you. Here's me. And there's Baji. Baji Baba. Okay. All right. Let me see how I can show you the picture as well. So let me do that. Let me turn this. Yeah, so there's the picture of the figure I was going to show you. See, going from the apple to the atoms, to the electron, to the protons and neutrons as well, to the quarks within the protons and neutrons, to the string. Waves hi at Baji, the cute kitty. Yes, he's right here. He's ready for you. He's ready. You can chill with him for a bit. Here you go, Baji. Here you go, Steven. Say hi to Baji. There you go. Aww. Baji's ready for some love. Oh no! Oh, I hope my phone is okay. I think it is. I think the phone fell. Cats are so special. I was so happy when I saw little Miss Luna back home today. Made my day. Hi, Baji. It's fine. Oh, look at this. Fuji's now sitting on the book. Elegant Universe by Brian Greene. Yay! Alright. We can say hi and bye, Baji. Good night to everybody. Good night. Thank you so much for being in the live today. Oh my gosh. And I got my new glasses. And here's Baji. Thank you, Steven. Thank you, everybody. Thank you, Peter. And please do check out the live episodes on my live tab on the channel. Yay! Yes, yes. Good night is correct. So here we go. Here's Baji saying good night for tonight. We will be back tomorrow. Good night. For tonight, we will be back tomorrow. Oh, here you go, Baji Baba. Baji Baba is ready for a good night. Oh, hee 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 hee. Hee 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 hee. Hee 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 hee. Hee hee hee. Oh, Fuji. Fuji, are you? Oh, Fuji's definitely sitting on the book. He likes it. He likes it as a seat. He likes the book as a seat. Oh. Okay, Baji. Ready to say goodnight? Good night. Oh, here's Baji. Good night. See you tomorrow. See everybody tomorrow. If you missed the live, then you can rewind. You can watch this thing if you rewind, or you can go to the live tab on my channel and see the whole thing. Bye bye. Looking forward to your comments. Yay. Bye.